Hey everyone, welcome back. Today we're going to solve an optimization problem using Python and SymPy inside a Jupyter Notebook. We're going to take a real cost function, minimize it, understand the calculus behind it, and then write the code step by step. So here's the problem that we're solving today. So the total cost to produce X large jewelry making kits and Y small ones is given by the equation, the function c xy is equal to 2x squared plus 6y squared plus 4xy plus 10. And since a total of 10 kits must be made, the constraint is x plus y is equal to 10. So we're tasked with determining how many large kits should be produced, determine how many small kits should be produced, and find the minimum total cost. So like we mentioned before in the problem, X represents the large jewelry making kits and Y are the small kits. So this is a classic constrained optimization problem. We're going to solve it using calculus by converting everything into a single variable function. And in order to do that, so because this constraint here is X plus Y is equal to 10, we can simply do Y is equal to 10 minus X. So this lets us plug everything into the cost function so it becomes a function of just one variable. So every time you see y in this equation, we're going to substitute it with 10 minus x. So now it's just an equation with one variable. Alright, let's write the Python code. So do import SymPy as sp. X is equal to sp.symbols. X is what variable that we're going to use. So this is our constraint as we mentioned earlier. And then our cost function. So the double asterisk will represent the square value. Plus 6 times y squared plus 4 times x times y plus 10. So when we run this block of code, it's going to give us the cost function with y substituted for each y value. So here I'm importing SymPy. I define x as my variable, and then I substitute y is equal to 10 minus x. And now the question's asking to minimize the cost function. And in order to do this, we draw on what we learned in calculus, which is we need to take the derivative. And this is because the minimum of a function occurs where the slope is 0, where the graph is flat. So since this is a continuous function, if you remember in math, different parabolas, if it's concave up, where the slope is 0 is where the point is not changing, where there's no increase or decrease in the function. So usually it's at the top of the curve or bottom of the curve. So now let's write so here, this line of code right here, dc underscore dx is equal to sp.diff parentheses cx. So we are taking the derivative with respect to x for the cost function. And this gives us the slope of the cost function. So by taking the derivative of the cost function, we get 8x minus 80. So now let's set the derivative equal to 0 this gives us the location of the minimum. So we need to find the critical points. So crit is equal to sp.solve So here we get a list, and in that list is 10. So when you run this solve function, it's going to give you a list of values, and that's the only value it gave us, which is 10. So what we're doing here is sp.eq_dc_dx. It builds the equation c prime is equal to 0. So this right here, c prime of x is equal to 0. That's all this is doing right here. And by placing this x right here, we are trying to solve for x. So these solutions are called critical points, and these are the places where min or max can occur. So like I mentioned before, the top or bottom of the parabola. Then we can write here so we're finding the first instance of what's in that list, which is x, which is crit 0. Since we know what x opt is, so 10 minus 10 is going to be 0. So we know x opt is 10, y opt is 0, and then we can output the values. So here, x is 10, y is 0, c opt is 210. So we plug the solution back to get the number of small kits, and we substitute into the cost function to get the minimum cost. So the optimal production plan is to have 10 large kits, no small kits, and the minimum cost is 210. So this means the cheapest way to produce 10 total kits is to make all 10 large and 0 small. And that's it. You just solved a calculus optimization problem using Python, SymPy through Jupyter Notebooks. Thank you.